In this video, we're going to introduce non-determinism. We're talking about finite-state machines, so we'll introduce non-determinism in terms of finite-state machines as we define what it means to be a non-deterministic finite-state automaton. But the concept is more general and applies to other sorts of machines like push-down automata and Turing machines. So we'll introduce non-determinism in its general form at this point. Let's begin our discussion of non-determinism by talking more carefully about determinism. What does it mean for a finite-state machine to be deterministic, or for any process to be deterministic? Well, essentially, it means that if we know the current state, then we know what the next state will be. Okay? We can go from the current state to the next state, and there is only one unique next state. There's only one thing to do next. Given that we know exactly what the state of the system is, there's only one place it could go to next. There's only one possible future. Okay? In the world of finite-state machines, our state, the state of the machine, is given very simply by what state the machine is in. And every moment in time is a discrete jump. So given that we know the current state fully, and with a finite-state machine that's quite easy and always the case, then we know where we'll go to in the next instant of time. Okay, there are no choices. You don't have any possibilities. If your input is, for example, an A, it tells you exactly which state you're going to next. So with a finite-state machine, or any deterministic process, there's always repeatability. If you start in the same state again, then you'll do the exact same thing on the same inputs. There's no randomness or variability. You don't need any magic to know what to do. You don't need to have a so-called oracle, some magical god that will tell you which choice to make. You don't need to guess. Okay? You can just go through from state to state based on the input. It's very simple. These machines are very simple to build because we know exactly what to do. And there's no cheating, too. What I mean by that is we assume that the machine does what it's supposed to do. In the case of finite-state machines, it's quite clear and formally defined as to what the machine is supposed to do. So we assume that the machine does exactly what it's supposed to every time and never malfunctions. So, of course, we have perfect repeatability. Now, what about normal computers? They are said to be deterministic by many people, meaning that there is no random behavior and they do the same thing each time. But of course, in real life, that's not quite the way it is, so I say forget about it. They're not really quite as deterministic as we'd like them to be. And as time has gone on and software complexity has increased, we're moving further and further away from the simple world of the 50s, 60s, and 70s where computers were much more deterministic. Modern computers take lots of random inputs. How the mouse is moved on the screen, how the keystrokes are hit, the timing of things. The net provides a level of randomness as well. So you cannot really repeat the exact same input to a program more than once. We also have random errors. And here I'm not talking about software bugs because those tend to be more or less deterministic. But I'm talking about errors that happen due to bits just randomly flipping on the disk or alpha particles slamming into the microprocessor. As our circuits get smaller and more delicate, they become more susceptible to random noise and perhaps even quantum fluctuations in the future. So as we have more non-repeatable events occurring and more random inputs, the idea of determinism in real computers seems to be we seem to be moving away from it. Also in the real world, we can't know the entire state of everything. In the real world, with physical particles of protons and electrons and so on, if you know anything about quantum physics, you know that we can't know the exact state of the system. And so that makes any question of determinism sort of moot for the real world. In the world of computers, we have vast memories, and both internal to the computer, the RAM, and external hard drives or whatnot. And because these constitute the state of the system, it makes it very difficult to recreate the exact state of a particular program. There's so many possible inputs and so much state information that to capture the state is in theory possible. Okay, after all, they're bits, they're either zeros or ones, but there's so many billions of these bits that it can be very, very difficult and challenging to recreate the exact same state. Another difference between the real world and the ideal world of digital computers is that in the real world, time appears to proceed continuously. There are no discrete jumps. In the world of computers, and particularly in the world of finite-state machines and Turing machines and so on, time moves in discrete steps. And so that aids in our understanding of determinism. We can still imagine determinism, I think, in a world where time is continuous, but in the real world that we inhabit, with physical properties the way they are, capturing the state is impossible for two reasons. One, there's just too much data. There's too much data to acquire. And second of all, the quantum properties of the universe make it impossible to know the exact state of the system and to reconstruct it anyway. Getting back to finite-state machines, let's now look at what non-determinism is. The idea here is that in a non-deterministic machine, given the current state, there might be multiple next states. Given the current state and whatever input symbol we're looking at as we are scanning a string, in a deterministic finite-state machine, there's only one next state. The transition function tells us exactly where to go. But with a non-deterministic machine, there might be multiple choices. There might be multiple states. There will be multiple states. And that's what makes them interesting. How do we execute a non-deterministic finite-state machine? Well, you can look at it in two different ways, and these are really kind of the same. We can imagine that we choose the next state at random, or we have some oracle that tells us the exact right one to go to. Or we can imagine that we try all of them somehow in parallel, or maybe we pursue them simultaneously, or maybe they're parallel universes, and in every universe a different choice is made. But the idea is that there are many possible next states given the current state of the system. I also want to say that we will use a couple different abbreviations, and I want to talk about these just briefly. Up till now, I've called finite-state machines FSMs, finite-state machine, and implicitly, finite-state machine means deterministic. But if we care about the distinction between determinism and non-determinism, we might want to use these initials: deterministic finite automaton or non-deterministic finite automaton. So DFAs and NFAs, D for deterministic, N for non-deterministic. We will now allow in our non-deterministic machines multiple edges coming out of a single state with the same label. So here we see, out of state 4, 2 edges labeled A and 2 edges labeled B. If we're in state 4 and we get an A, do we go to 5 or do we go to 7? Which one do we take? If we get a B, do we stay in 4 or do we go to 6? This machine, or this part of a machine, is non-deterministic, and so the machine is non-deterministic. We're also going to allow something we call epsilon edges. An epsilon edge is an edge that's labeled with the empty string, or the epsilon symbol. Normally our edges have to be labeled with symbols from the alphabet, but now we're going to allow these epsilon edges. And the idea here is that you can take an epsilon edge without scanning a symbol. So if we're in state 2 and we're looking at an A, we can go to state 3 and scan the A. But we can also go to state 9 and not scan the A. And then maybe there's a transition from state 9 that tells what we do if we see an A. Likewise, if we could go to state 4, we can take these epsilon edges if we want. If we're in a state with an epsilon edge, we can take that edge without scanning any inputs. It's an optional edge, if you will. Let's look at our first example of a non-deterministic finite state automaton. Here we want to recognize the language that contains strings that contain 0, 1, 1, 1, 1, 0 as a substring. So any string that contains this sequence of 6 symbols should be accepted and recognized as part of the language. And it's pretty straightforward to build a machine that does this if we have non-determinism. So here we see some transitions, 0, 1, 1, 1, 1, 0. And so, but it's non-deterministic because if we get a 0 from our initial state, do we stay in the same state or do we move here? Or effectively we can do both. So here's an example string, and we can scan this by saying 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1. Okay? Now I was able to get from the initial state to the final state, following edges and scanning every single element in the string. So therefore, this string should be accepted. I knew which choices to make. There were a lot of bad choices. For example, if I had started off and gone 0, 1 with the first 2 symbols, I would have been stuck. But I didn't choose that. I chose a pathway through this finite state machine that did reach an accept state. So there are a lot of bad choices, but in order for a string to be accepted, here's the key. All we need is one way to reach the accept state. So here's our definition. If there's any way to run the machine that ends with an accept, then the non-deterministic finite automaton accepts. So all we have to have is a single pathway from the initial state to a final state that matches the string, and that string is accepted by the machine. You can see that in a non-deterministic finite state automaton, there are many choices. And the question is, which one do we want to try at each decision point? And one thing we could do is just try them all, systematically try all possible combinations. Might be a little bit tricky to keep track of everything, but we could, in theory, try all possible combinations. Or another way to look at it is we could just guess the right choice at each point. Now, we're humans and we have additional intelligence beyond what a finite state machine has, so we can maybe use that intelligence to make the right choice based on other information, our ability to look ahead in the string and reason about the string. These are all equivalent. These are both equivalent. It doesn't really matter whether we try them all systematically or whether we somehow know via an oracle or some magic which choice to make. If we can find a pathway from initial to final state that matches the string, then the string is accepted by the machine. Okay, here's another way to kind of look at what's going on. I've made a couple of graphs here to show the difference between determinism and non-determinism. In these may look like a finite state machines, but they're not. Okay, these are trees, and these represent choice points. So at each, and time goes down here. So we start up here, and we have only one possible thing we can do in a deterministic machine. So this is a linear chain in a deterministic machine. There's only one thing we can do. We have only one choice to make, or equivalently, we have no choice. Okay, we have to do exactly one thing. Now, in the non-deterministic machine, we have choices. Okay, so in the initial state, we might go this way to one state, or we might take another transition to another state. Okay, keep in mind, these little circles here do not represent states in a finite state machine. These are pathways in executing the finite state machine. So if we had taken this choice, we might have 3 more choices. If we had taken the second choice, then apparently we only have 2 choices. And in the non-deterministic machine, some choices that we make might end in reject. Okay? Many will end in reject. Some might get stuck. We saw in our previous example that there were some states where there was no possible edge to take. Okay, just to repeat that, if, for example, I had taken 0, 1, and then when I see the third 0, I'm in state C, there's no choice here. Okay, so I'm effectively stuck. With deterministic machines, we have to have a dead state, and we assume there's a dead state. But with non-determinism and non-deterministic finite state automata, we don't necessarily need that dead state. There can just simply be no possible choice to take. So that means we can get stuck at certain points. And getting stuck is equivalent to rejecting. But all we need is one set of choices that will lead to acceptance. We just need one possible way to get from the initial state to a final state. And then we will accept the string. I want to examine this idea of the computation tree or the choice tree a little bit more carefully. And I'm going to use this finite state machine as an example. You can see that it's got an epsilon edge, so right off we know it's a non-deterministic machine. We've also got 2 edges labeled 1 coming out of A, so there's additional proof that it's non-deterministic. So it doesn't really matter what this thing accepts. But let's look at the string 0, 1, 0, 1, 1, 0. Can we get through this machine with that? Well, 0, 1, we could do 0, 1 and get us to B after the second symbol. And then we can do 0, 1 again and 1, 0. So we can see that this string is an element of the language that's recognized by this machine. There may be other ways to get from the initial state to the final state with this string. But there's at least one that I've just shown, 0, 1, I'm sorry, let me start again, 0, 1, 0, 1, 1, 0. So that means this string is accepted. Now I've drawn down here the choice tree again, and I've fleshed it out in full detail. Sometimes this is called a computation tree, same thing. So let's see how this works. Over on the right side, I've got my string 0, 1, 0, 1, 1, 0. And at each point, we're in some state, and we have certain choices we can make. The first symbol is a 0, okay? The first symbol is a 0. There's only one thing we can do, and that's stay in state A. The next symbol is a 1, and there are 2 things we could do. We could stay in state A, or we could go to state B. Now if we go to state B, there's an epsilon edge to C. So we can immediately go to C. But our next symbol is a 0, and if we go to C, we're stuck. We can't do anything. So that branch ends before we get to that 0. On the other hand, if we stay in A and B and see that 0, well, in A, we remain in A. In B, we go to C. Okay, now what happens? We see a 1. In state A, we can remain in state A, or we can move to state B. And in state C, we go to D. So in A, we can move to B. In C, we can move to D. D is a final state, but we still have more of the string to go, so we don't accept at this point. Now again, we can take that epsilon edge from B to C at this point, if we choose. And so if we're in state A and we see our 1, we can stay in state A, or now we can move to B. If we're in state B and we see a 1, there's no place to go. But if we had taken the epsilon edge to C, we could move on to D. And so that's what I show here. And if we're in D, we can stay in D. And now we could either be in state A, B, or D. And if we see our final 0, well, in state D we stay there, and that's an accept. So there are two ways to get to accept. And if we're in state B, we could take our epsilon edge immediately to C, but then the 0 we would not be able to go further with the 0. If we had stayed in state B, we see a 0, we go to state C. If we stay in state A, if we're in state A and we see a 0, we stay in state A. At that point, our string is exhausted. Our input symbols, we're out of input symbols, and we've reached the end of our string that we're trying to determine whether to accept or not. And so these branches do not accept, and they fail. However, we found two different ways to reach accept, so this string is accepted by this language, by this finite state machine.